Hi, you're listening to Hear This Idea, a podcast showcasing new thinking from top academics at the University of Cambridge and beyond. Kent Berridge is a distinguished professor of psychology and neuroscience at the University of Michigan. Through experiments on rodents, his research addresses questions about how pleasure is generated in the brain, the relation of fear to desire, and what causes addiction. This is a wide-ranging conversation and we cover a lot of ground quite fast, so I think it'll be helpful to quickly explain some key words in case some of them aren't clear. So, cues are mentioned a lot, and what psychologists mean by cue is just some signal that anticipates a reward or an outcome. So animals, ourselves included, learn to associate cues with outcomes, like the bell that signaled food for Pavlov's dogs. Dopamine is a neurotransmitter that's a chemical messenger in the brain which we know is related to reward and addiction and probably lots of other things. It's sometimes called the molecule of more. The mesolimbic system, or pathway, sometimes called the reward pathway, releases dopamine and it's associated with reinforcement learning. The amygdala is a small area of the brain, it's right in the middle, and it's involved in processing emotions and in particular fear. And the last one is valence, or hedonic value, which literally just means how good or bad something feels. So higher valence, higher hedonic value, more intrinsically attractive or good. That should be everything by way of definitions, but of course this episode's write-up goes into way more detail. Our conversation starts off fairly technical. We go over what is meant by reward learning and the dopamine prediction error. Stick with it because it's a very useful backdrop for understanding the second half of the episode, where we get to talk about Professor Berridge's experiments involving rats, cocaine, and lasers. Enjoy.
My name's Kent Berridge, and I study wanting and liking in the brain. I'm usually at the University of Michigan in Ann Arbor in the States. I really want to understand what causes pleasure in the brain, what in the brain truly causes pleasure, because in neuroscience we've had a number of candidates that turned out not to cause pleasure after all over the years. We want the real pleasure generators. I'm also interested in what causes wanting for pleasant things, that wanting and liking for a pleasant thing usually go together, but the brain has different systems for doing the wanting, different from the liking, and we want to understand how they work, what wanting really is all about. What's an actual experiment? Well, to find what in the brain is causing what psychological process, it helps to be able to turn brain systems on and off painlessly, and there is technology to do that. We would do animal experiments that are painless. We have to do animal experiments because in humans it wouldn't be possible to turn brain systems on or off even if it were painless, except in a very few rare clinical cases where, say, people are implanted with electrodes or drug cannula. But in animals it is possible to painlessly turn brain systems on or off and sort of see, does this cause enhanced liking for things? Does it cause wanting for things? What causes what in the brain? That's what we do.
So you're interested in the mechanisms behind wanting and behind liking, but can you just explain a bit about the difference between the two as you understand it?
Right. Well, the difference between liking and wanting isn't something that we had theoretically posited before we started the experiments, and we never actually really expected it to be different. Liking and wanting, they're used almost equivalently or interchangeably. If you like something, you typically want it. If you want something, you expect to like it. They go together. They could have been synonyms, and in neuroscience usage, I think they were treated as synonyms. But when we started looking for brain mechanisms of liking, the most famous candidate when we started was brain dopamine. Lots of reason to believe that brain dopamine was pleasure liking in the 1980s. But in our hands, looking at it in a slightly different way than other labs had looked, it wouldn't behave like pleasure liking. And understanding how dopamine could counterfeit pleasure liking in so many laboratory approaches and clinical approaches, yet not be liking in the way we were looking at it, led us to think about the different labs were looking, the approaches that they were using. And when it became more convincing that dopamine wasn't actually liking. The question was, what was it doing psychologically that could counterfeit or mimic wanting in lots of behavioral test procedures? That's what put us on the difference.
Got it. So let's dig into this. What is the prediction error hypothesis, and how does it relate to dopamine?
Right. The prediction error hypothesis originally came out of a sort of marriage between computational approaches to reinforcement learning, computers that were learning tasks, and neuroscience electrophysiology in the 1990s. Wolfram Schultz, who was here at Cambridge, sort of pioneered the electrophysiology, and several computer scientists who were writing programs for computers to learn new events noticed that one particular kind of equation called the temporal difference prediction error equation, an algorithm that computers could use to learn incrementally to do the same thing, to do something if it was rewarded. The dopamine neurons that Wolfram Schultz was recording from fired in ways, they became active in ways during learning about rewards in monkeys that obeyed the prediction error equation. So from the 1990s through about 2010, prediction error meant the temporal difference model of learning, the temporal difference equation for learning. In the last 10 years, it's morphed a little bit away from that for several reasons, but that was its original formulation. Conceived in neuroscience, the prediction error hypothesis said dopamine neuron firing was a mechanism of reward learning, and the way it contributed to reward learning was by every dopamine burst of firing to an unexpected reward contribute a prediction error increment in the learnt value of cues for that reward, a small increment that could add together with multiple repetitions to finally produce a strong prediction of the reward. That was the original notion.
Great. And very simply, do you think it's right? And if not, which of your experiments bear on that?
Right. Well, it's a debate that's gone on now for 20 years whether it's right. I believe that the prediction error equation is right, and the model is right within very limited circumstances. It does predict the behavior of the dopamine system within limited circumstances. Those circumstances are when a reward value is being determined solely by new increments in learning. If we start with a meaningless cue and we learn about it gradually time and time again, that's a situation where the eventual value of the cue for reward has been learned incrementally. In that situation, the dopamine neurons follow the temporal difference model beautifully.
Would you mind giving us an example, either in the real world or an experimental example of where that prediction error hypothesis would then be applicable under the circumstances you gave?
Right. So the original demonstrations were Wolfram Schultz's when he was working in Switzerland, and then he moved to Cambridge. And what he showed was that a monkey who would enjoy fruit juice as a reward, when the first time it saw a new cue, a meaningless cue that it hadn't experienced at all, the dopamine neurons might fire just a tiny bit to that cue, but they wouldn't fire again if the cue was presented a second time. However, if the cue was followed by a fruit juice reward, then the dopamine neurons would fire in a big burst to the surprising fruit juice reward that was surprised because the monkey hadn't known it was coming. If you paired the cue with the reward several times, gradually the dopamine neuron would start to fire to the cue itself that predicted the reward. And after a number of trials, it fired vigorously to the cue that predicted reward. And when the actual reward itself finally came a few seconds later, the dopamine neuron didn't fire again. So the firing had moved forward in time to the predictive cue. This step-by-step transfer is exactly what's predicted by the incremental step-by-step temporal difference equation, this gradual transfer in reward prediction value. So the prediction error was the original surprise, and as the dopamine firing moves to the cue, it's the cue itself, which is the surprising and informative and predictive reward event that equation has given it. Where the equation starts to go wrong, and maybe another phrase to introduce here, was model-free versus model-based kinds of learning. Model-free meant that you learned just an increment of stronger prediction, stronger reward prediction, stronger event prediction. It didn't really matter what was predicted. What was important was the quantity of the prediction strength. That's what the dopamine neurons firing could represent. In that view, you don't have to know much about the world. You don't have to have a model, a cognitive model of the world and where things are in it. So the dopamine neuron, the temporal difference equation, was classically model-free. In the computer programming world, it's model-free. You don't need to know more about you don't have to model the world. However, it's clear now that the dopamine neurons actually are not entirely model-free. They are model-based, and they start to change their firing in ways that the prediction error equation hasn't told them yet. So here's an experiment. This one, there's a number that have come from Cambridge and from other labs, but this one was from our lab. It was an attempt to say whether the learned value of a cue was simply a matter of its incremental experiences with reward, or whether it could be computed all anew in a model-based fashion. This draws on Dead Sea saltiness. We talked about a little bit earlier in this. Dead Sea saltiness is disgusting. It's salt water that's the salt concentration of the Dead Sea, which is 3 times saltier than regular ocean water. It's disgustingly salty. And in this cue experiment, a rat learned 2 cues for 2 events. One cue, a lever popped out of a wall, and it was a cue that would predict a squirt of sugar water, not saltiness, but sweet sugar water into the mouth. And as this cue happened a number of times, the rat would, as soon as the lever popped out, the rat would jump on that lever and start gnawing and nibbling on the lever. It was a cue for sugar. Another cue would pop out of a different wall, a different lever with a different sound, and this cue, this lever, meant that a squirt of Dead Sea seawater would squirt into the mouth. The rat would gape and shake its head, and it would stay as far away as possible from that salty lever. This went on for a couple of days, and the rat had learned it very well. It would jump on the sugar lever every time it came out, and it would avoid the salt lever. Now, by temporal difference models, the sugar lever had been paired incrementally with a positive value that grew step by step by step by step to this high value, so now it was attractive and jumped upon. The salt lever had learned a decremental value, a negative value, again and again and again, so now it was repulsive. Then one day, the rat woke up in a new appetite state that it had never experienced before because it had received 2 hormones the night before. These are hormones that mimic the brain signals of salt appetite, of sodium deficiency. If you and I were living on a vegetarian diet, a vegan diet entirely with no salt added, we would develop sodium deficiency, and our ancestors in the savannah definitely had sodium deficiency. Deer outside, squirrels outside often have sodium deficiency. But you and I have never had it because there's loads of salt in the foods we eat, more than enough. And that's true for the rat's food too, so it's never been in a state of salt appetite. But it woke up one day because it had been given 2 hormones that mimic the brain signals, the brain hormones, the brain active hormones of aldosterone and angiotensin II that tell the brain we're in a state of salt appetite. On this day, even Dead Sea saltiness would have been delicious and liked to the rat, but the question wasn't that right away. The first question was, what would the rat do when the cue for sugar or the cue for saltiness came out? Would the rat have to learn that the nasty cue for Dead Sea saltiness was no longer nasty because Dead Sea saltiness was no longer nasty? It had never had saltiness in the liked state yet. The saltiness had always been nasty. So on this day, the cue came out of the wall, and what happened was the rat jumped upon the salty cue as soon as it came out, just like it was the sugar cue. Jumped on it and nibbled on it in all the same ways. It didn't have to re-experience the saltiness. It didn't have to relearn the cue value. There's no way that the temporal difference equation can give you this. In fact, the temporal difference equation, you'd have to start from a negative value, come back up to neutral, and then go slowly back up to positive. But this is a model-based, brain-based computation of incentive value. At the same moment that the rat jumped on the cue, if we looked at the brains later, we could see that the brains had activated the ventral tegmentum that gives rise to the dopamine system, the nucleus accumbens. It seemed that the dopamine system was activated at that moment. These are ways in which the system just stops obeying the equation. So people debate about what the dopamine system actually does. We still debate about it. To the degree people think it's prediction error now, they would, I think most of them, 9 out of 10, say it's a model-based prediction error. But what they mean by that is often complicated and needs to be specified.
Got it. So if the straightforward prediction error story is true, you would take the rats in the salt-deprived state a lot of time and a lot of repetitions to learn to associate the cue of salts with a good thing rather than a bad thing.
Exactly.
But they leap on it, so it's not quite...
Exactly. It's telling us that the brain does something different and it uses the dopamine system to do something different. What I think, by all the prediction error versions of this hypothesis for dopamine is thought to be the mechanism of the learning. What I think is that the dopamine is the mechanism of the learnt value, or rather the value of the learnt cue. And the value of the learnt cue sometimes is the learnt value, the sum of all previous learning. But as in the salt case, it's sometimes the sum of more than just the previous learning combined with new brain states. Every time when you're hungry or you're full, when you're thirsty, when you're in various kinds of states, the value of cues change. And the brain is doing this, the dopamine system is doing this. This is value that interacts with learning, but it isn't reducible to learning, and the dopamine system is doing it.
So could you explain your incentive salience theory and how it's different to this prediction error story?
Right. So incentive salience, it sort of stems from a psychological theory of motivation that goes back to a number of psychologists, Robert Bowles and especially Dalbert Bindra. In the psychology of motivation and the neuroscience of motivation, if we went back to the 1960s, most neuroscientists thought that motivation was a matter of nasty drives, unpleasant drives. Hunger is unpleasant. It makes you eat food so that the hunger would go away. Thirst is unpleasant. It makes you drink so that that nasty thirst goes away. Drug addiction, withdrawal is unpleasant, so you take drugs to make that go away. Drive reduction was the notion. But a number of experiments came along in the 1960s and 70s to say that actually drive reduction, even though hunger is nasty, drive reduction is not the way the brain works. Rather, the brain is really all about rewards and incentives and motivation. The taste of food is far more motivating than just making hunger go away. If you are fed intravenously or intergastically, you're loaded up with nutrients, but it may not satisfy your appetite. Your appetite is sort of focused on the act of eating. And so rewards are important, and cues for reward turn out to be very, very important too. Animals and even people sometimes will scrabble after cues for reward. We get pulled in by cues for reward, and a lot of our motivation is triggered by cues for reward. Dalbert Bindra had pointed this out, and when I say a cue for reward, you might notice that it actually is often essentially a Pavlovian cue that predicts reward that very much maps onto the prediction error manipulations in which cues predict rewards. Cues take on value of their rewards. They're attractive, they spur appetite, sometimes they're sought out themselves. And incentive salience, in a sense, is this notion that the cue is both wanted and liked in some ways as though it's the reward. It can be pursued and even consumed. Rats will eat a metal or wooden cue that's paired with sugar rewards. They'll try to eat it anyway, as though they like it and they'll work for it. All incentive salience does regarding this Bindra notion of cues as rewards is it pulls apart the wanting of that reward from the liking. And that really came out of the dopamine experiments that we mentioned. Well, I'm not sure we've described them. But the notion that the dopamine system was not the liking meant that the wanting for a learned cue was somewhat separable from the liking that cue could trigger. And dopamine seemed in particular to be mediating only the wanting. Incentive salience is the technical term for the kind of wanting that the dopamine system is doing. Why incentive salience? Well, because it's an incentive. The cue is an incentive that you want, but it has particular properties. It's hard not to look at a reward cue that you want at that moment. It pulls in your attention. In human psychophysical experiments where they track eye movements, for example, if people are trying to sort among different little things they're looking at, reward cues will pull in the eye movements and involuntarily pull them. And there's lots of attentional features that go with it. So it's salient in this sense. Reward cues become salient, and that's part of their attractive power. And they take on the wanted properties of the wanted reward. So that's a little bit separate from the hedonic impact, the liking of the reward. It's also separate, I should mention, from a kind of wanting that's more our normal everyday use of the word wanting. Normally when we say wanting, we think you have a sort of a cognitive image almost of what it is you want. You can imagine it, you can describe it. This is a declaratively accessible, a consciously accessible goal, a representation of that goal. And you expect to like it, and you may know how to get it. Incentive salience can go along with this, but it doesn't have to go along with this. And it can occur without a conscious goal. It can also occur in opposition to conscious goals. And an addict who's trying to give up a drug consciously, that's their conscious intention, their want in the usual sense, but finds themselves tempted in ways that even they find hard to understand or explain. That's a case of mesolimbic incentive salience wanting occurring in opposition to a conscious want to abstain. In a sense, if you think of human neuroimaging experiments on reward, the person goes in, and if they're shown something that lights up their reward system, that's a brain signature of the reward. Now, all these psychological processes are happening simultaneously in them, but not all parts that light up are participating equally in all the processes. Some are driving a particular process. Mm-hmm. What sensitization does is it pulls just the wanting component of reward out of the liking and the learning and the expectations and sort of magnifies that while leaving the other components to be whatever they were to begin with. That's that sort of difference in addiction.
So it sounds like the thought is it's possible to really want something because dopamine is predicting incentive salience, whilst at the same time not particularly liking it when you get it, or even knowing that you won't like it. That sounds kind of strange to me. Like, is there an example you can give?
Well, it is strange, and I think in most cases the dopamine system behaves more reasonably. It goes along with the things we actually like and that we do expect to like. So normally those things all cohere. They evolve to cohere, the systems. But it can come apart. Because there are these separate mechanisms, the processes are separable. So addiction might be one case in humans. If we imagine an addict who can say to us, if you can imagine this being possible, the person saying, well, I know I'm addicted and I know it destroys my life. And I don't want it to destroy my life anymore. And in fact, this particular drug, I don't really find it all that pleasant. And I'm not in withdrawal. I haven't taken the drug for weeks or for a couple of months, so I'm not in withdrawal. And yet at certain moments, especially when I'm sort of in a social setting where I used to take the drugs and someone lights up or shows me the drug, I have an urge. And if I'm emotionally stressed or if I'm emotionally excited when I see this, I may have an overwhelming urge. And sometimes I've relapsed and given in to the urge, and I can't give you a reason why I did that.
Just the general idea is that this dopamine system helps us to want the things which ideally we'd always end up liking. And normally those two things go together. And that's why it's there in the first place, just because it's useful for us. But sometimes wanting and liking comes apart. And addiction is an example of that, where you might just know you're not going to like it, but you still really want it, right?
Exactly right, yeah. Yeah, I think it's fair to say that the mesolimbic wanting system evolved to give motivational oomph, usually to the things you cognitively want. And that's helpful, but it can come apart.
Okay, so we have liking and wanting, but also it sounds like two kinds of wanting. One is the mesolimbic wanting system, and the other is a more kind of high level, I'm going to reason about this and decide that I want it for, because I have these goals and aims and whatever. But the mesolimbic wanting system, this is like more basic, right? This is a kind of just gut drive, right? Is that right?
It's a good way to describe it, yeah.
So one question you might be interested in asking is why creatures have a capacity to experience pleasure at all? Why not just want lots of things but not particularly enjoy them when you get them? Wouldn't that just lead to the same behavior?
Yeah, that's a wonderful question. It's a major fundamental question, and I don't think lots of us would love to have the answer, but none of us have a very strong answer. However, the kinds of answers that are given often are such as Tony Dickinson, who's a fine psychologist here, now emeritus, suggests that pleasure exists because it essentially allows brain-wanting systems that might have evolved for one thing, say food, to experience a new pleasant event, like, say, drugs or a new invented social accomplishment in our evolutionary history, and to enjoy that event and to sort of bring to bear the brain-wanting systems that evolved for the old things onto this new target, basically giving us new targets of desire. And that's a very, very good answer, I think a very plausible answer. One could probe it further, but that's a very good answer.
Sure. Yeah. So the thought is, look, simple creatures, it's possible to hard code what they want and like because they experience a fairly narrow repertoire of things that are good for them, things like food and shelter. But creatures as complex as humans or even rats, we live in such a complicated world with lots of potentially new things that would be good for us that couldn't have been predicted or foreseen by evolutionary mechanisms. So it's just way more useful to have this really flexible way of learning to want all kinds of new things, and that is what pleasure does for us.
That's exactly right, and that's probably the best answer we have for why pleasure exists.
Should we talk about the lasers?
Yeah, let's talk
okay.
about lasers.
So in the last few years, you have been experimenting on rats using lasers and sugar pills. Could you tell us a bit more about what that involves?
Sure. We're doing this to try to understand how the brain controls the focus of wanting, the target of wanting, and the narrowness or the breadth of wanting. In ordinary life, you want different things at different moments. Foods now, drinks something later. Maybe people who enjoy drugs take at certain moments. Wants come and go, and it shifts in their focus. In addiction, the target of wanting becomes sort of focused and fixed and intense. So we'd like to understand what it is that's controlling the shifts and the focus and the narrowness of focus when it becomes narrow. A new technique that is useful for turning on the brain in ways that get at this question is optogenetic laser activation of the brain. This was discovered about 10 years ago. People like Carl Dieseroth at Stanford really pioneered this. They realized that photoreceptor molecules, which in our eyes are activated by light, and when the light hits the molecule, it changes the shape of the photoreceptor molecule so that it activates neurons that the molecule is attached to. This happens naturally in our eyes, these photoreceptors. Dieseroth and his colleagues realized that photoreceptor molecules occur in nature, like even in algae and in other creatures, simple photoreceptor molecules, but nonetheless, if they were within a neuron, these simple photoreceptor molecules, they could activate that neuron if light were to strike a particular neuron. And Dieseroth and colleagues invented two special things to make this happen, to activate neurons. The first thing they did was to recognize the photoreceptor molecule was created by genes. The algae that had the photoreceptor had a gene that would produce the photoreceptor. So they took the gene for that photoreceptor molecule from the algae and they put it into a simple virus that they gutted so it couldn't reproduce. They removed a little bit of the gene from the virus so it couldn't reproduce, it couldn't spread, it couldn't infect multiple cells. It could only infect where the virus actually physically was placed in the brain or in the body. So they put a gene into the virus that would do this. And then the second thing they did was to arrange for light to reach the neurons through an optic fiber that was attached to a laser light, giving a highly intense, in this case, blue light. It turns out that these photoreceptors from the algae are specifically turned on by blue light. The way they do it is and what we've done with the technique, if you take a tiny droplet of the virus, that has the gene for the photoreceptor. And in an anesthetized animal, or perhaps someday in an anesthetized person, that tiny droplet of virus solution was put in one particular brain structure, like the amygdala. That virus would infect the neurons just where it was placed, in that tiny location in the amygdala. And that's what it happens in our experiments. And then in the same surgery, in the anesthetized rat, a tiny optic fiber is implanted in the amygdala and attached to a little head cap that's permanently fixed. When the rat wakes up and recovers, it feels no pain because the fiber is permanently fixed, the head cap is permanently fixed, the virus is gradually being expressed by the neurons. The neurons are making their photoreceptor. And after a couple of weeks, the neurons of the rat have the photoreceptor just in its amygdala. And now if you turn on the laser attached to the optic fiber that's implanted in the amygdala, it will illuminate the neurons in the amygdala. Those neurons will fire action potentials because the photoreceptors change their shape. They allow exciting, positively charged ions to enter the neuron. The neuron becomes excited, and that's what makes neurons fire. What we do is we pair this now with the rat. We let the rat learn that its laser comes on, its amygdala fires, when the rat is earning a particular sugar pellet or a particular squirt of intravenous cocaine, or sometimes even a particular nasty event like touching a rod that sticks out of the wall, that if you touch it gives you an electric shock. The rat doesn't have to touch it, but the rat could touch it, and if it touches it, it'll get the electric shock plus the laser. Or if it takes the intravenous cocaine by poking its nose into a little hole that triggers cocaine, it gets the cocaine plus the laser. Or if it presses a lever that earns it a sugar pellet, it gets the sugar pellet plus a laser. If this happens a few times, say 10 or 20 times, in a half hour, and if it happens maybe for a couple more days, what happens is the rat now will eagerly choose and work for just that laser-paired sugar, or just that laser-paired cocaine, or just work and touch that laser-paired shock rod that gives it a slightly painful electric shock. And it becomes almost obsessively, addictively chasing this laser-paired sugar or cocaine or shock, and will work for cues that are paired with this same laser-paired event like the shock. So it seems motivated and focused on it. And in our experiments, we've asked the rat, is it the laser they seek? The answer is usually no. They don't really care about the laser by itself. We ask, does the laser make the sugar more pleasantly liked? The answer is usually no. Does it make the shock simply always pleasant? And the answer is no. It can actually make shock worse in some other cases. So what the laser seems to be doing is multiplying the incentive value of sugar or cocaine and actually transforming the motivational value of the shock from feared into wanted. It's transforming the brain's representation of the motivational value of these particular narrow targets, making them incredibly valuable, yet not making them liked, and we believe not making them expected to be liked. In fact, the rat has to actually expect that the shock rod is going to shock it in order for it to be attracted to the rod. If we turn off the shock, the rat won't be attracted to the rod anymore. It'll lose that attraction. So it has to expect to be shocked and get the shock, and to create these maladaptive, addictive types of wants.
Okay, I think it's worth spending a bit of time going into some more detail on this experiment because it's really interesting. So first of all, there's a way of taking the molecule in eyes, which helps us see light. There's a way of implanting it in very specific areas in the brain, and specifically in this case in the amygdala of the rats. And then you can shine light on it and stimulate that area, which is amazing in itself. And then we have two kinds of experiments. One involves learning cues associated with nice things like sugar pills or cocaine, and the other one involves cues associated with something nasty, in this case an electric shock. But let's just talk about the cocaine example, for instance. So what does that experiment look like?
Right. Well, the cocaine experiment might be where the rat has a choice between cocaine and, say, sugar pellet. It could earn either cocaine or earn a sugar pellet. And many rats in this situation want to earn both, and they will earn both, sort of equally. It isn't that cocaine is always super. But we'll bring 2 rats into this situation, and for one rat, we'll put the laser, we'll pair the laser with earning the sugar, with the cues for the sugar too. So whenever it earns the sugar, it gets the laser plus the sugar. Whenever it earns the cocaine, it gets the cocaine alone. And that rat will come to prefer and seek out only the sugar. It'll ignore the cocaine as though the cocaine were worthless by comparison to this laser paired sugar. A second rat will come into the same situation, but for this rat, we'll pair the laser with the cocaine and not with the sugar. And this rat will come to obsessively pursue only the cocaine as though sugar were worthless. It seeks out only cocaine and ignores the sugar. So in a sense, we've created one rat into a sugar rat for whom cocaine is worthless. The other rat's created into a cocaine addict for whom sugar is worthless. It tremendously amplifies the value of these paired rewards. And yet the same rat, if we ask it to earn the laser by itself or go to a place where the laser will happen, it doesn't seem to want to do that usually. It's as though the laser by itself were worthless. It's just when the laser is paired with the cocaine, it makes that cocaine and its cues tremendously valuable. Or when it's paired with the sugar, it makes that sugar and its cues tremendously valuable. It's an interaction between the brain activation caused by the laser and these particular stimuli.
So that's surprising in itself, that this laser does something to get the rats to far prefer the cue associated with the laser. But things get even more surprising when you now pair the laser with the electric shock. So can you talk about that?
Yes. So when we were finding all of these attractions, we were wondering what could sort of set the boundary conditions for these attractions. What we knew, and everyone in neuroscience knows, that the amygdala is involved in more than desires. It's involved famously in fears. And we were almost concerned that we were getting always such strong desires out of the amygdala stimulations. We were wondering if it could be afraid. So when we started the shock rod situation, it was our way of asking the rat in a very mild situation where the rat never had to get a shock unless it voluntarily tried it. Would the amygdala stimulation make it more afraid of the shock rod? That's what I actually expected when we started. To my surprise, to the surprise of the PhD students who were actually doing this study, Shelley Warlow and Aaron Nofziger, instead of making the rats more afraid of the shock rod, the laser pairing seemed to pull them into the shock rod. They'd go back to the shock rod and go touch it again and again and again, and sometimes even nibble on the shock rod. It was as though the rod was becoming just an irresistibly attractive cue. They'd hover over it, they'd sniff it eagerly, and they'd inevitably shock themselves again and again. We'd take the rat out after several minutes of this, and after it's gotten just a few shocks, because we don't want it to keep on shocking itself. That's how it manifests, this maladaptive attraction. Once it was there, it was something we had to follow up. It was a demonstration that wanting could occur even for something that was nasty, even in the absence of liking, and even for something that you knew was going to be nasty. Important implications for addiction and possibly for some other maladaptive ones.
So worth just being clear, I know you've already mentioned it, but the rats aren't voluntarily shocking themselves because they really like the laser, because you could just shine the laser without a shock or with a kind of fake dummy shock, and they don't show any of this kind of behavior. So somehow the laser is making them more attracted to this stimulus, which they obviously don't like. That is quite surprising.
That is the paradox, absolutely, that the laser makes the nasty shock rod more attractive, incredibly irresistibly attractive, yet the laser won't make a neutral rod, a dummy rod that looks like a shock rod but just doesn't give any electric shocks. If we pair the laser with that, the rats are not attracted to that at all. So it isn't adding value. The laser doesn't add value, which is the traditional neuroscience and psychology way of thinking about value acquisition, to add value. It's rather transforming value a little bit like that Dead Sea salt cues value was transformed that we talked about earlier. Here the brain is doing it almost instantly through this brain activation.
Got it. And the other mysterious thing is that, as you mentioned, we normally associate, or at least often associate, the amygdala with fear and with learning aversive behavior. So why doesn't the laser just make the rats more fearful of the electric shock compared to the control condition?
Right. In neuroscience, we have a presumption that the brain is put together in a way that obeys what's called localization of function. One way of rephrasing localization of function is to say one neuron does one psychological function, a different neuron does a different psychological function. Every neuron has its own psychological function, and you can trust it to do that. Much of the brain is organized this way. But I think the amygdala is telling us that in it, some of its neurons are not dedicated just to fear nor to desire. Rather, turning on these neurons with a laser triggers a motivational process that can be built into desire or can be built into fear, depending upon a number of things that are going on in the world as well as in the brain at that moment of activation. So it's sort of a challenge to us to understand how valence itself, goodness versus badness, hedonic goodness versus hedonic badness, is represented and generated by the brain. We don't have good explanations for this. In a sense, this kind of phenomenon is a surprise even to neuroscientists. There's one or two other phenomena that fall into the same category of valence flips, but they're relatively rare. And our scientific minds are not prepared to deal with this kind of thing. But the phenomena, in the end, will force us to deal with these and to come up with better explanations. At the moment, I think all I could say is that there's the possibility that some neural systems and some psychological processes actually can become building blocks that can flip into either fear or into desire. Motivational salience. We've talked about incentive salience, something that reward cues can acquire. Feared cues have a fearful salience. It's hard not to look at them and not to feel threatened by them. They'll instantly grab your attention. Motivational salience is something that's shared between the two. The only funny thing about motivational salience is that it's hard for it to be neutral. It can be positive as incentive salience. It can be negative as fearful salience. And it can flip between positive and negative fear and desire. But it's hard for it to be neutral. It's as though it has two preferred modes of existence and it's got to flip if it's going to be activated at all. I think the amygdala is telling us that it has this kind of motivational salience process that's flippable in valence. But we need to understand much more, of course, about the features, the nature of this process.
Got it. So it sounds like, if I'm getting this right, there are two interesting things from this experiment. One is that, at least in rats, you can separate wanting and liking to such an extent that you can get rats to really, really want something that they very obviously really don't like. And the other interesting thing is that we have this view that specific areas in the brain and even specific neurons, they just have one job. Here's what they do. They're associated with positive or negative valence, for instance. But because it looks like you can flip valence, is as if the very same areas of the brain, or even the very same neurons, are coding for or associated with a positive reaction, hedonic reaction in one case, and a really negative reaction in the other case. And that's quite surprising.
Yes, that is the idea. To explain valence, I think neuroscientists are going to have only two kinds of concepts. One would be the building block concept, the notion that a process could exist that could be flipped into valence, fear, or desire. That would be motivational salience. The other possible explanatory concept would be that the neurons actually are always valence themselves, but they have multiple modes, a particular neuron, different patterns of firing, different neurochemical states. Whether it's multiple modes or shared building block processes, this is something we'd love to understand better.
And this is just an open question now.
That's right. I think in science we start with phenomena that sort of make us realize something is happening that we hadn't expected, and then we have to try to understand what it is that is actually happening. And that's where we are at this stage.
So it definitely sounds like all of this research has some relevance for addiction, and maybe even addiction in humans. So how do we transfer over what we've learned from these experiments in rats to humans?
Right. Well, I think there's sort of two steps in applying this wanting liking framework to addiction in humans. The first step happened 30 years ago when, as we began to realize that the dopamine system was a wanting system rather than a liking system. My colleague Terry Robinson had pointed out that the dopamine system in some individuals would become permanently sensitized by addictive drugs. And to be permanently sensitized meant that the dopamine system became hyperreactive to the drug and to drug cues. It wasn't always hyperactive all the time, but it was hyperreactive to the drug and drug cues. And a hyperreactivity in dopamine could produce a sort of hyper want, a more intense want than the rest of us ever experience because it is more intense in its neural mechanism. Not everyone is vulnerable to this. At street doses, many individuals won't be sensitized. Even among rats, there's massive individual differences. Many rats won't be sensitized at a particular dose, but some will. And some may be so vulnerable to this that they can become even spontaneously sensitized by life events like stressors or other emotional events, and behavioral addictions could result from this. So sensitized wanting is the first step to addiction. But the next question, as we think in neuroscience to try to explain addiction, the competing theories today are theories like, well, addiction is an overly strong habit, or addiction is an overly strong negative emotional state, negative hedonic state of withdrawal, or just life, stress, and bad circumstances that we try to self-medicate by taking drugs to make that go away. In what these experiments are telling us, especially the new experiments, is something about the nature of the motivational process that's involved in addiction. If we think it's an overly strong habit, then we'd want to reduce the strength of the habit. If we thought it was negative states alone, then making the negative states go away would cure the addiction. If the addiction is a kind of wanting that can occur even when there's absolutely no liking at all, even in the face of a disliked but yet wanted target, then that's telling us that that's the motivational process that we need to recognize could be involved, and we'd have to come up with ways to deal with that. So it's telling us something about the psychological nature of addiction, or at least its potential nature, and clarifying what it is we're actually grappling with if we want to treat addictions.
Got it. So I'm just trying to understand this. So when you talked about sensitized wanting, the idea is that you can be addicted to a drug, stop taking it, and you'll experience some withdrawal symptoms, and they'll go away predictably. But even many years later, you might see a cue for that drug. You might see someone, lighting up, or you see the same drug, and you experience the same strong wanting as you originally did. So that doesn't go away as fast as withdrawal does. Is that the idea?
That is the idea. The sensitized wanting system, once it gets sensitized, it turns out to be just extraordinarily long-lasting. And so even in rats, if you stop taking the drug, tolerance and withdrawal go away, but sensitization actually gets stronger if you stop taking the drug for a month or so. It shows something called incubation. So now the cue is even more potent. And this could have a lot to do with why people who are addicts can go through detox programs, which takes them through withdrawal, out of withdrawal. They're no longer in withdrawal. And yet when they come out of the program, they still can be, in many cases, enormously vulnerable to relapse, especially cue-triggered relapse, under conditions of emotional excitement. These are exactly the conditions that promote the maximal sensitized dopamine response and could produce in them an urge that's so strong that it even surprises them, stronger than the cue has been triggered in other states. It's not a surprise that some people find that hard to resist.
And it's not as if people relapse because they just decide to change their mind, and they suddenly now have some belief that taking the drug will be good for them, or that they'll really like it, and they forgot how much they liked it. It's possible to totally believe that you won't like it at all and that it's not remotely good for you, but you feel this really strong urge. That's the difference, right?
That would be exactly the conclusion, to the extent that the shock rat experiment results will transfer to the human addiction case, right, which is very, very possible that it does transfer. So this is the universe of ideas in which we operate. That's what the results tell us is possible, conceivably.
And then more broadly, there are these two kind of poles when it comes to views about addiction in humans. One is that it's just a kind of choice, much like all the other choices we make in life. And another view is that it's a kind of compulsion or even disease, something we don't have control or choice over. From what you've learned from your experiments on rats, what might they teach us about which view is most accurate?
Well, I think both views have a claim. I mean, this is a very lively debate today. Should addiction be thought of as a brain disease, or should it be thought of as an ordinary choice? And in favor of the ordinary choice, it's very clear that the decision to take drugs at any moment is a choice that's influenced by ordinary choice factors like punishments and incentives. People can be paid to abstain, and they'll abstain more. People in some situations where punishment is sure and certain will abstain until it's no longer sure and certain, the punishment. So there is a choice. But if the incentive sensitization hypothesis of addiction is true, then it means that an addict has changes in their brain that put the dopamine system into a hyperreactive range that's stronger in its reaction than the rest of us ordinarily experience. And that's giving them an urge that's stronger than the rest of us ordinarily experience. Any of us could experience this kind of urge if you wanted to. If we were starved enough, starved for weeks and months, so that we really were in the situation of prisoners, say in a concentration camp, then cues for foods can become irresistibly attractive. There have been volunteer studies where this has been induced in people, and the people start to dream about food and to obsess about food, and cues for food become very, very tempting, even for a motivated person who's strongly trying to resist. That's a hyperreactive wanting system, mesolimbic hyperreactivity to wanting that any of us can produce. But what's special about an addict is that they could be having a similar wanting response to their addictive cue, even though they're not starving, even though they're not physiologically different from any other person. But in their brain, they are slightly physiologically different. That gives them this capacity for that cue. A starved want in an unstarved brain. That's my notion of an addict. And because this is so, the consequences can be so severe if a person relapses and spirals down in some cases, that to me makes this special state, it's fair to call it a brain disease in a sense. There are diseases that are diseases of extreme parameters with deleterious consequences. Incentive sensitization fits into that family.
Now, it's easier to see why drugs like cocaine are addictive in humans like they are in rats, because there's a kind of clear causal pathway that relates to dopamine. But humans get addicted to all kinds of things: gambling, gaming, the internet, shopping. And we very rarely get addicted to other things. So I don't get addicted to brush my teeth, but I do it regularly, right? So what is it that addictive activities have in common that make them addictive?
What they all have in common is that they all have a special ability to activate the mesolimbic dopamine system, even in non-addicts. So there's hundreds of human studies where people are put into scanners and allowed to play gambling games, and winning money lights up our mesolimbic system in all of us. The kinds of consumer items that will light up our brain systems are exactly the targets that this sensitization is going to key into if we're vulnerable to the sensitization. So it's just like with the rats. Cocaine and sugar and even shock are powerful potential targets for laser amygdala pairing. So in humans, If we're vulnerable to sensitization, it will be addiction, or it will be drugs or gambling or shopping or sex and pornography or things in this relatively limited universe of incentives that become the targets of the behavioral addictions in those who are vulnerable.
Got it. And just briefly, so addiction is a particular kind or class of disorder, but does your research map on to any other kind of disorders?
Well, it is an open question, and it's not something that we do apply this to other human disorders. We do animal experiments to understand what in the brain does what psychologically. But a number of people in psychiatry and in human clinical psychology have applied the wanting-liking distinction to other disorders. So, for example, in depression and in schizophrenia and Parkinson's disease, for decades, it was in textbooks that these conditions involved what was called anhedonia in depression, anhedonia in Parkinson's, which meant literally the incapacity to experience pleasure. Because if you're depressed, pleasures have no value. But studies that have been done in the last 10 years a number of studies have shown that, well, actually, these patients, they are capable of pleasure liking, but they have no value in the sense that they aren't motivating. Whether they're liked or not, neither foods nor family interactions nor social accomplishments have any zest in life. They're not desirable. They're not desired. It's a want. It's been suggested this is not anhedonia, but rather avolition or a motivational anhedonia, really a selective loss of wanting, not of liking. So that's one kind of clinical implication. There are other clinical conditions too, but you sort of see the logic.
So I was wondering how all of this in the case of addiction in humans might translate to recommendations for treating addiction or for policy, if you had any ideas about that.
Right. Well, it is certainly the goal of all studies of addiction to try to come up eventually with treatments. The difficulty is that understanding the nature of what goes wrong in addiction, although crucial, both for understanding addicts and for eventually finding the solution, understanding what goes wrong doesn't in itself give us a way of reversing what's gone wrong. Now, what we could say is what we'd like to do, if sensitized wanting is the problem in addiction, we want to reverse the sensitization of wanting, yet leave normal wanting, as well as leave normal liking and learning about rewards. The difficulty is that, yes, you could suppress sensitized wanting, but only through sort of sledgehammer manipulations like drugs that block dopamine, that also reduce wanting and motivation for all of life's rewards. It's not a viable approach. At the moment, the most effective treatments are probably the cognitive behavioral therapy treatments and treatments like mindfulness, augmented a bit with medications for addictions, but the medications by themselves are not very effective. In the future, it's conceivable to imagine that it will become possible to reverse these brain changes. There are actually a few animal laboratories with results that are suggesting that in rats, it is possible with a combination of optogenetic manipulations and drugs to selectively reverse sensitized wanting. Those manipulations, even if the claim is true, are not manipulations we could yet do in a human. They wouldn't be either ethically possible or effective at the moment. But it's conceivable that in the future it could be transformed into ways that would interact, say, with transcranial magnetic brain stimulation that isn't invasive, uses magnetic fields, interacting with brain manipulations that don't have to involve invasive probes permanently implanted. It's conceivable to imagine that it might become possible, but that's down the road, and I wouldn't even hold it out within the next 5 to 10 years.
So we've just got a couple more questions. The first one we ask all our guests is, what view, and in this case in psychology, have you changed your mind about?
Oh, 1,000 things. It's constant a changing of mind and realizing I was wrong. The first big one was I was absolutely convinced that dopamine was pleasure. When I began my career, I loved that hypothesis, and we started our experiments intending to add one more little bit of evidence to the conclusion that dopamine was pleasure. It was painful, literally painful, to have results that didn't fit that. The silver lining was the wanting hypothesis that came out of it later, but that was a process. And in so many ways, I would say in the course of my career, even before I started in science, I was sure from the beginning of topics that I was interested in. And I think earlier in my career, I took that to mean also there were topics I was not interested in. What I've learned over the course of my career is that a number of the topics that I thought I was not interested in were actually absolutely crucial to the work I'm doing now, ranging from social psychology to pharmacology and molecular biology. So if I were starting again, I think I'd say to myself, yes, identify what you want, what you are interested in pursuing, but don't wall off the fields outside and keep a really active interrogation of other fields, because you never know what's going to turn out to be useful.
Great. And the last question is, what 3 books or papers or films would you recommend to anybody who wants to find out more about these topics?
Well, there's so many sort of sub-questions that we've talked about. I think any student might want to look at Wolfram Schultz's recent review on dopamine, published, say, from 2015 to 2017. That would give you the prediction error hypothesis from the mouth of the inventor on the neuroscience side, the original inventor of that hypothesis. So that's a marvelous thing. There's also some excellent papers on the Cambridge habit theory of addiction from Trevor Robbins and Barry Everett and David Belin and others who are in the psychology department on that. If you're interested in wanting and liking, papers, my lab's papers are all available on my lab's website for free download. But I'd suggest perhaps a chapter with Richard Holton, co-authored Holton and Berridge several years ago. That might be a good introduction for philosophically inclined students. Terry Robinson and I had a paper on wanting and liking and incentive sensitization, meant for broad psychological audience, any psychologist. That's in American Psychologists, I think 2016. Berridge and Robinson, American Psychologist, 2016. And that's on the website too.
Professor Kent Berridge, thank you very much.
Thank you.
That was Professor Kent Berridge on dopamine, addiction, and neuroscience. As always, if you want to learn more, you can read the write-up at hearthisidea.com/episodes/Kent. There we go into more detail on the theories and experiments described in the episode, and you'll find links to Kent's recommended reading and to his lab's own website. Also, we'd be really grateful if you could leave an honest review on Apple Podcasts or wherever you're listening to this. We're just starting out, and at the time of recording, we don't have any reviews yet. Your